Hello and welcome to CO 738 Probabilistic Methods. Today we'll be discussing concentration inequalities. So what are concentration inequalities? Well, generally we say that a random variable x is tightly concentrated, if for all t at least 0. The probability that x minus its expectation, absolute value, so that's the distance there, is at least t is at most on the order of e to the minus t squared over e of x plus t, with some constants there, so an omega. So generally we're looking for this exponential decrease in the probabilities there, so for these tails. So this is large deviations. You'll note the t squared, so if t is roughly square root of the expectation, this doesn't really tell much, so we can't expect to know much concentration within around a square root of the expectation. But if we're further apart, if we're further than that, than many standard deviations, then we might expect this exponential decrease. And this is much better than what we get from, say, Chebyshev's inequality in the second moment method, as we'll be experiencing this exponential decrease. So that will be tightly concentrated, and such inequalities are generally referred to as concentration inequalities. And today we'll be discussing a few of these, namely Chernoff Bounds, Hoeffding's inequality, and Azuma's inequality. They won't exactly be of this form, but they will be when the expectation is roughly on somehow the number of independent variables it depends on, or if there are some of independent variables. So we'll see that as we go. So before we get to Chernoff Bounds, let me start with a beginning. If x equals x1 plus xn, so there, where each xi is independently and uniformly chosen for -1 and +1, then for every a greater than 0, we claim that the probability that x is greater than a is at most e to the minus a squared over 2n. So we're claiming that, indeed, roughly we get this exponential decrease if we take the sum of independent plus minus 1 variables. So you might believe this, of course. You might realize that this would behave roughly like a Gaussian distribution, and so in the limit this should indeed be true, but we're going to go ahead and prove this to show off a basic method. So how does this work? Well, we'll let lambda be arbitrary and greater than 0. We'll choose that later to make the proof work. And for every I and n, the important thing to note is what is the expectation of e to the lambda xi. So we're going to take look at these exponentials. So what would happen there? Well, xi is either plus or minus 1 with probability half. So half the time I get e to the lambda, and the other half the time I get e to the negative lambda. And you sum that up, and you might recognize that as a function. It's namely the cosh function there, the hyperbolic cosine. So we'll have cosh of lambda, and what good is that? Well, if you look at cosh of lambda and you look at its Taylor expansion, so what is it? You're taking the even terms of the exponential, so you're getting the sum from k equals 0 to infinity of lambda to the 2k over 2k factorial. And it's easy to note, actually, that sum, term by term, is at most the following sum from k equals 0 to infinity. You can take the lambda to the 2k and write it as lambda squared to the k, and the 2k factorial on bottom is actually at least always bigger than 2 to the k times k factorial. And now if you stare at that sum, what you'll note is that then that's lambda squared over 2 to the k over k factorial, which is e to the lambda squared over 2. So a nice fact that you might not have known is that this cosh lambda is always at most e to the lambda squared over 2. So what good is that? Well, now we get to the point, is to actually go ahead and prove from these expectations. And generally, I'll just point out that using these exponential expectations is an improvement, therefore, over Chebyshev's in the second moment method. Really, we're looking at higher moments here. So we're really looking at this Taylor series expansion of all these moments. We're incorporating all of the higher moments when we're using these exponential moments. So moving on with that, we also know that e to the lambda x, well, if x is the sum, then the sum goes in the exponent, and we can write this as a product of I and n of e to the lambda xi. And since the xi are mutually independent, so are their exponents there, e to the lambda xi. And hence, if we take the expectation of e to the lambda x, this high moment there, then we can write it as the product, only because of the independence, of e to the lambda xi. Since e to the lambda x is this product, and since they're independent, we can move the expectation inside. And then we'd already established that e to the lambda, the expectation there was cosh lambda for each one. So we get cosh lambda to the n, and that will be most e to the lambda squared to the n over 2 by what we had just done. All right, so now we have an upper bound on this exponential moment. What good does that do? Well, here's the important part, is that x is greater than a if and only if e to the lambda x is greater than e to the lambda a, right? So if we take this exponential transform, it preserves when you're greater there. And so we have that the probability that x is greater than a is equal to the probability that e to the lambda x is greater than e to the lambda a. And now we can work with the exponential moment. So we saw this trick before with second moment methods, passing from somehow the linear variables maybe to quadratic ones. Here we're passing to exponential variables. So we're going to pass to this different variable, this different probability, and now we're going to work with that. And it's helpful, we've already calculated the expectation. We calculated it and then we upper bounded it. And so now we can apply Markov's inequality. Why? Because e to the lambda x is always non-negative. So just as in Chebyshev's, where we looked at the square and then that was non-negative and we applied Markov's to derive Chebyshev's, here we know, okay, we have e to the lambda x is always non-negative, so we apply Markov's. So what would that tell us? It tells us that the probability that e to the lambda x is greater than e to the lambda is at most the expectation, there, e to the lambda x, divided by e to the lambda a. And then if we plug in our bound from above, we get this is at most e to the lambda squared n over 2 minus lambda a. So we've done all that, and we've gotten this very general expression that's an upper bound on the probability that x is greater than a. And now we have to do the choosing of the lambda, right? So lambda is arbitrary, and we want to minimize this. So actually setting lambda equal to a over n, you can check we'll minimize that and give the desired result. So the left term there will be a squared over 2n, and then we'll have minus a squared over n, so you get the minus a squared over 2n as desired. So that was the beginning. So that was a very simple result showing that this method of higher moments can be quite useful. And more generally, if x is any random variable, then we could always use this fact that the probability x greater than a is the probability that e to the lambda x is greater than e to the lambda a, which by Markov's would be at most the expectation of e to the lambda x divided by e to the lambda a. So that would always be generally true. And there, what did we do for the plus minus 1 variables? Well, we were able to upper bound that expectation of the exponent there, and then choose an appropriate lambda. More generally, the core idea of so-called Chernoff bounds is to select the lambda that minimizes this function for a given variable x. So get upper bounds with the expectation, and then choose and accordingly a lambda that would minimize that to get good bounds. And this might depend on the assumptions of the variable and so forth. Probably here is their most useful form, and we'll omit the proof here. So again, this comes Chernoff bounds, given the choice of the lambda and the variables, lead to really a whole suite of bounds. There's no one particular Chernoff bound. I'll just tell you what I think is generally the most kind of useful. So it goes like this. If x is the sum x1 up to xn of random variables, where each xi are independent 0, 1 random variables, so they're Bernoulli. So each xi is a coin flip. Those coin flips are not necessarily uniform. They could be weighted, so each could have a different pi. Then for every delta in 0, 1, the probability that x is smaller than 1 minus delta, the expectation, is at most e to the minus delta squared, the expectation over 2. So what is this saying? This is generally referred to as somewhat the multiplicative form. So if I want to know how far I'm below the expectation, and again, x goes between 0 and something there, so delta really shouldn't be like more than 1, then the probability there, if I want to say I'm a tenth smaller as a proportion of the expectation, then indeed, I'll get a tenth squared there, but if the expectations are found for lots of different variables, as long as kind of the expectation is large, I'll get this exponential decrease there. And that would actually accord with the somewhat more version of tightly concentrated we talked about, because basically your t would be delta e of x, and so you could view this as t squared over 2e of x. And similarly, that's the lower tail. For the upper tail, the probability that x is at least 1 plus delta, so it's a delta proportion higher. The math ends up being a little bit different because of how you can bound exponentials. But instead of a 3, instead of a 2, you could take a 3 there. So you get delta squared e of x over 3, which is slightly worse bound, but it's again, still a constant. Now that only applies when delta is in 0, 1. So if you're only looking between 1 and twice the expectation. More generally, you'd get something like the denominator being 2 plus delta there. So you'd, again, restore that formula I had from before, where if you viewed t as delta e of x, you'd get roughly t squared over e plus t with some constants. And you kind of need that plus t, you would need that plus delta, because somehow if you're trying to get good bounds when you're really, really large compared to the expectation, you need it not to be quadratic, but rather linear. All right, so that's all we want to say about Chernoff bounds. So let's move on. So we won't prove that, we omitted the proof. It's a bit more involved, but now we want to go to general variables. So that would work if we had 0, 1 random variables. What if you have random variables that are allowed to range? So an important one is called Hoeffding's lemma from 1963, and it deals with this case. So if x is a random variable such that a is at most x is at most b, so x is always between a and b, then the expectation of e to the lambda of x minus e of x, we claim that this is at most e to the lambda squared b minus a squared over 8. So how should you view that in context? So as you saw with the Chernoff bounds, we're generally interested in upper bounding these exponents, these expectation of the exponents. And why I have x minus e of x there? Well, we could write it on the other side, since that would just be a constant, or you could think that we'll normalize the variable so the expectation is 0. Then what we would be interested in, we want this kind of e to the lambda squared property on the side with some constant there. So here we'll have an 8. The constant doesn't matter too much when we get around to our bounds. What we are interested in is we're going to use that range factor. So we'll end up with a b minus a squared there, and so that's somewhat natural. As the range gets bigger, the expectations could get larger. So if we were in the case we were before, where we were plus or minus 1, then b minus a squared would be 2, and we get lambda squared over 2, which would then correspond to that analysis we did for just one plus or minus 1 random variable. So let's go ahead and prove Hoeffding's lemma. Now it gets a little bit complicated, so we're just going to prove the weaker bound where we replace 8 by 2. I'm just going to do this for simplicity, as it's a slightly nicer proof. It's not really that much longer to prove the 8, but you have to do a bit more work. So let's do the simpler version. Then what can we do? We'd assume without loss of generality that e of x is equal to 0. And so we can just do that again by shifting. So that's without loss of generality. And then what would we know? Well, the expectation is 0, so that means the range of where the variable is, namely a and b, the a would have to be at most 0 and b would have to be at least 0. And we may assume without loss of generality that the absolute value of b is at least a, otherwise we'd flip the variable. And then what can we do? Well, now we have to do some magic. We choose an appropriate function. So here I'm going to make a function f of x, which will be b plus x over 2b times e to the lambda b, plus b minus x over 2b times e to the minus lambda b. Now where does that function come from? Really, this is, if you think about it, it's a line, kind of the chord, intersecting e to the lambda x at x equals negative b and x equals b, right? So if you put x equals negative b in there, then you end up with e to the negative lambda b, and if you put b in there, you get e to the lambda b. So this is indeed hitting that e to the lambda x in exactly those 2 points. So that's how I made the function. I chose it like that, but it is a linear function. It's a line. And now the important part is that e to the lambda x is convex for all x. And what would that mean? If it's a convex function and have this line between 2 points, it means that e to the lambda x is at most f of x for all x for that chord. So for all x in minus b to plus b. And now we're almost done, because then if we know that e to the lambda x is an upper bound, then when we take the expectation of e to the lambda x, since x lives inside this interval minus b to plus b, we know that that's at most the expectation of f of x taken over really from minus a to b, weighted with x. But by linearity of expectation, and since the expectation of x was assumed to be 0, we'd have that e of f of x, so evaluated like this. What do we get? Well, we get that we'd have b plus the expectation of x, and b minus the expectation. So we'd have these constants that will just come out. And then if we're weighting the little x, right, where x lives on that, then actually we know that indeed this will go to 0. So the linear parts will end up getting washed out because their expectation is 0. And what does that give you? Well, b over 2b is a half, so we get e to the lambda b, and we get e to the negative lambda b, and also over a half. So that's the cosh of e to the lambda b. And hence, we get that the expectation of e to the lambda x is at most the cosh of lambda b, which is at most e to the lambda squared b squared over 2 by the analysis we did before. And so then this is at most e to the lambda squared b minus a squared over 2, since b minus a is strictly bigger than b. And then that concludes the proof. So here we did it with the simpler factor of dividing by 2. But if you wanted to get to the 8, you'd have to do a little bit more work. So it's the same basic idea. You pick a chord, but you pick a chord not from minus b to b, but from a to b. And then you have to do a bit more work where instead of the cosh, you would also have to use the hyperbolic sign, the sinh there. And then figure out with Taylor series some upper bounds for that. But generally, in all of our bounds for applications for probabilistic methods, we don't particularly care about the constants and the exponents, so I thought I'd just show this somewhat easier proof. But if you care about really improving it, you can go read the more detailed proof. So what good is that? Well, then Hoeffding in 1963, when he came up with this better bound, coming from, again, the Chernoff Bounds, the method there from 1952, was able to apply this to get somewhat of a better inequality than we'd have for Chernoff Bounds, or at least more, not a better inequality, but rather a more general one. So, namely, if you had independent variables, so if you had x was a sum of independent variables, and each one satisfies xi is in an interval ai to bi, then for every t greater than 0, we can show that the probability that x minus e of x is at least t, and there I have it without absolute values. If you want absolute values, you'd have to do both sides, but you could just flip x and put a 2 on the right side if you want to do that. But anyway, that if the probability that x is much larger than its expectation would be at most e to the minus 2t squared divided by the sum of these interval sizes, so bi minus ai, but squared. So what would that give you? That tells you if if bi minus ai was 2, then you get 2 squared, so you get 4 n times. So this would just recover essentially the simple bound we did before. It would imply essentially up to the constants the same as kind of Chernoff bounds if the expectations were more on the order of n there. So this seems like a very nice bound, and again, it's general, so you could assume each is bounded by the same, but this is even more general. It's allowing some flexibility with the AIs and the BIs. Okay, so again, a nice inequality. It's very general because as long as they're independent, but they can really do whatever they want distribution-wise between inside their interval. We're just using that somehow we're a sum of these bounded variables. So for a sum of many bounded variables, then we kind of expect this exponential decrease. And you might wonder, why do these bi minus ai squares show up? Well, that's quite natural if you think that all these inequalities should remain even under transforming the variables, right? So if you scale the variables up or down, and then you'd be scaling t at the same, you'd be scaling their intervals. So if you see a t squared there, then the intervals should also be with squares. So I found that to be a good point of order when thinking about these inequalities. They should always work under scaling. And so that gives you a sense of the units. So let's move on to the proof of Hoeffding's inequality, where really it's the same. We're just going to use Hoeffding's lemma. So by Hoeffding's lemma, we would know that if we look at xi minus e of xi, then we know that e to the lambda of that, the expectation, is at most e to the lambda squared bi minus a squared over 8 for all I. So that's the work we've done. And now, since the xi are independent, we know that the expectation of e to the lambda x minus e of x, then that would just be the product of all those by the independence. Then you take the product of their expectations. So then we get this upper bound of e to the lambda squared, but we get the sum over the i's of the bi minus ai squared over 8. And then using this Chernoff method, now that we have a nice upper bound on our exponential moment, we can know that the probability that x minus ex is at least t is at most e to the lambda, the expectation of e to the lambda x minus e of x, divided by e to the lambda t, and then you rewrite that so you get an extra minus lambda t in the exponent there. And then if you set lambda, again, you kind of figure out what the minimum should be, what to do to minimize, so you'd set lambda to be 4t over the sum of the bi minus ai squares, and that would give the desired result. So do you see what happened there? You get 4t squared for lambda, so that'd be 16t squared, but you divide by 8, so you get like a 2t squared there, and then you end up dividing through by the square of those intervals, twice, so that would cancel, be on the bottom, and similarly on the other side you get a minus 4. So you get 2 and minus 4 gives you that minus 2 up top. So that's Hoeffding's inequality and the proof. So the basic idea again of Hoeffding's, once you have that nice lemma to bound the exponential moment for one bounded variable, then we can apply this Chernoff type method and choose lambda appropriately to indeed end up proving Hoeffding's. Let's move on to the second half of the lecture, where we'll tell you about something more general, which is a bit strange, but is quite useful. So it's called Martingales. So a martingale is a sequence x0, x1 up to xm of random variables, such that for all I, at least 0 and at most m, the expectation of xi plus 1 conditioned on xi minus 1 down to x0 is equal to xi. So this is just a definition, but what does it mean? So we're somehow saying it's a sequence of random variables where if I condition on the past, the expectation of the next one's the same as where we were before. Let me put this maybe in more illustrative terms. You'd consider, so the motivation of where these were defined was, consider a gambler in a casino whose fortunate time I is xi. So say he walks in x0, and you could say, maybe it starts with 0 money or whatever his initial stake is, and suppose that all the games are fair. That means their expectations are 0. Then I claim the sequence forms a martingale, right? So he comes in, and if it's really a fair casino, which, nowadays is not true at all, but if, say it was, then whatever money he has, the next game he plays, he expects to retain the same amount of money, to have the same in expectation. And the point is that this holds no matter the betting strategy of the gambler. You might think the gambler just goes in, but the gambler, of course, could change the betting strategy. He could even have it depend on previous outcomes or bets. For example, the bettor could do the thing where he doubles the bet until he wins. So every time he loses, he doubles. That's a betting strategy that would depend on the past and the previous outcomes. And yet still, it would be true that in expectation, we always expect to be keeping the same amount because these are fair games. And so this would form a martingale. And so it's kind of worthy of study because it's not an independent variables there. It's the sequence where there could be a lot of dependence, but just somehow conditionally that next step is kind of a bit memoryless, that no matter what has happened, we expect the next step to remain the same. So that's a martingale. You might ask, what about examples of martingales? I gave you one with the casino fortune. Maybe a more useful one in general is something called a Doob martingale. And there's not a precise definition here, but roughly it's a due martingale for a random variable is a martingale obtained by exposing information about x, where I say x is the random variable, in a monotonically increasing fashion. So what do I mean by that? So you think of this variable x, I need to give you a sequence from that. So you would think that, let's say x0, I use no information about the variable, and then somehow if I've set up nothing, so I've made no assumptions, then the expectation of x0 would just say be the expectation of x. And then what do? We begin thinking of one particular trial and exposing the information. So maybe you think x depends on different independent variables. So I would tell you, okay, here's the first coin flip, here's the second coin flip, and so on. I slowly begin to expose the information, and then as time goes on, you would get closer and closer to the truth. So while xn has full information, would end up, if n is where you end up, would have full information, and hence the expectation at that time would be actually the trial itself, the xn. So there's this idea that as we expose the information, that the expectation of, if we don't know what the next step will be, as we expose it, the expectation's the same there, but then as we expose it, we get more and more information. So it's a useful mental construct, and you can apply this to graphs quite nicely. So for example, there's the edge exposure martingale, is the due martingale for GMP made by exposing the edges one at a time in a prescribed order. So you might ask, where do these martingales come up in probabilistic methods and combinatorics? So here's a nice example. So you have the Erdős random model, GMP, and so you think you have all these different coin flips for the edges. Here you do an exposure martingale where we end up saying, okay, let's order them in any prescribed order, and now GMP is all graphs all at once, but now maybe I want to expose one at a time. So I view this as a martingale, and maybe we're tracking some random variables such as chromatic number, clique number, etc., some graph functional. And what I do is I'd expose them one at a time. So I say, okay, now here's the first edge. Is it in or out? Here's the second edge. And as we go, this will indeed form a martingale where we're looking at the expected value of that function as we unveil the information. And so it goes from being the expectation over everything, where we have no information, to eventually being the actual function when we get to an actual graph at the end. And similarly, there's something called the vertex exposure martingale, which is the due martingale for GMP, made by exposing the vertices one at a time. And what do I mean by that? Because the vertices aren't the trials, I would mean the edges incident with a vertex to previously exposed vertices. So I kind of think of exposing subgraphs in a nested fashion. So of course this would just be a special case of the edge exposure martingale. So I won't go through that in much detail, but maybe we'll end up using it later to do examples for random graphs. But it's a nice construct, and maybe lets you more easily think about this due martingale idea of exposing information. And that's quite a natural one. It's a bit weird because we're doing it somehow for something that you've done it all at once, maybe just for one random variable, but by exposing it over time, you can view it as a martingale. So what good are martingales? What good is all of that? Well, the main tool we have is something called Azuma's inequality from 1967 that says let 0 equal x0, so we're going to assume that we start at 0, and then up to xm be a martingale. So say we have a martingale where we know we start at 0, and you tell me that for every I in m, xi minus 1 is at most 1. So I have a martingale, and I promise you we can never fluctuate more than 1. So imagine the gambler, but they can never somehow win or lose more than $1 at a time. Then I claim that for every lambda greater than 0, the probability of xm, that xm is at least lambda to the square root of m, is at most e to the minus lambda squared over 2. So again, what is that suggesting? That, if we somehow thought of it as actual heads and tails coins, as we had before, that kind of random walk, then we would expect not to get much further than square root of m steps from 0. But here, there's no assumptions that it is plus or minus 1 uniformly. There's no assumptions that they're independent steps, just that they're somewhat memoryless. And then the claim is that we still get this kind of exponential decrease. So let's prove Azuma's. Here, I'm going to set alpha to be lambda over root m, and you'll see why later. So that's just a choice for the future. And the key is, I have this martingale, but I actually view for every I and m, I think of yi, where the difference between xi and xi minus 1. So that's how much I win or lose in step I. And I view that as a random variable. And then the point is, we assumed that yi is at most 1 in absolute value. And crucially, by definition of martingale, how much I win or lose, the expectation of yi given the past is 0. So right, that was the definition of martingale, that at each step I expect to neither gain nor lose. And given those assumptions, we can use Hoeffding's lemma. So now I don't look at yi, but I look at this yi conditioned on the past. I view that as a random variable. Then I pass to the exponent. So I think of e to the ayi conditioned on that random variable. And again, the expectation of yi on that conditioning was 0. So the exponent will satisfy Hoeffding's lemma, and we'll get, that's at most e to the a squared over 2. And now we're almost done. Why? Now we just need to do a little bit of trick with conditional probability and this memrelais property. Namely, we know that a to the x m, the final value, is of course the sum of what I gained and lost at each step. So it's the product of e to the ayi. Now the issue is that these are not independent, right? That's the point. What I gain and lose at each step may not be independent because I might have changed my strategy. So I can't just write this as the product and be done like we were in Hoeffding's, but I can be slightly more clever. So what I can do is I can take them one at a time. So I look at the very last step, right? So we have the product of the e to the ayis, and then I have e to the aym. I have that kind of last exponent. And I think about that, and I realize, well, I have this expectation. I can actually then write it out conditioned on the expectations of what I've had before. So you could do that, but what you'll end up noticing then is, then we can move the expectation back inside. And then what is that expectation? It's at most e to the a squared over 2. And so then we end up so basically at each step we end up picking a factor of e to the a squared over 2, e to the a squared over 2. So you kind of argue how far can it move in the last step, that it's going to be at most e to the a squared over 2. And then you do that to the m minus 1 step and the m minus 2 step and so on, using induction, and you get that it's at most e to the a squared m over 2. So this is quite clever and nice. And then you're basically done, because we now apply Markov's as we've had before. So again, the probability that xm is at least lambda squared m. You do, that's the probability that e to the axm is at least e to the a lambda squared of m, which by Markov's is the expectation of e to the axm divided by e to the a lambda squared of m. And now we use the upper bound from above, so we get e to the a squared m over 2 minus a lambda squared of m. And now this is where we use our cleverly chosen a there to end up getting that these will end up canceling out, and then we'll end up getting e to the minus lambda squared over 2, right? So we picked lambda to be a to be lambda over square root of m, so we'll just get a minus lambda squared on the right and a lambda squared over 2 on the left. That'll give you a minus lambda squared over 2 as desired. So very similar to how we do Hoeffding's, or how we had done before in our simple example using Markov's. But here we need that exponential upper bound, and we can indeed get it through using the conditional assumptions. So then, more generally, so that I did where each one was at most 1 bounded, but more generally, if you do the exact same proof, and in the same way as we did with Hoeffding's, if you said that every xi minus 1 is at most some ci, so I can only gain or lose at most ci in step I, then you get basically the same thing, where you'd have an e to the minus lambda squared over 2 the sum of the ci squareds. So I won't prove that, it's the same proof. And again, I'm only doing one direction, so this is only the upper tail. But the lower tail would work by reversing the negative, so you could actually bound the absolute value there, and then just have a factor of 2 by the union bound. So I won't state that. For our last thing I want to do, let's actually go back from Martingales to functions. So let x be a random variable that, say, depends on n independent trials, x1 up to xn. We say x is c Lipschitz if changing any xi changes x by at most c. So what is this saying? Don't think of a martingale, think just of a random variable, depending on some independent trials. You could think coin flips or not. But here I'm not suggesting it's the sum at all. So in Hoeffding's, we had the sum. Here it just depends. It could be in a very strange way. But you just promise me that no matter how it depends, that whenever I change the outcome of one trial, change any xi to some different value for it, no matter what happens, that if I only change one trial, it changes by at most c. Then we call this being c Lipschitz. Okay, so that's generally this idea that of a variable that doesn't change much in differences. And then the claim is you get this what's called McDiarmid's inequality from 1989, which is really a special case of Azuma's. So if you have this random variable that depends on n independent trials, and if you're C Lipschitz, then you get tight concentration in a sense. You get the probability of absolute value of x minus e of x being greater than lambda squared of n is at most 2 times e to the minus lambda squared over 2c squared n. So what does that mean? No, I've used absolute value there, so I put a 2 on the other side. So if you're square root n away. Now it's not clear that's really tight concentration if the expectation isn't really somehow on the order of n there. It's not clear that that's really quite good. But if you kind of imagine that square root n is what we want to show, that the number of trials somehow is roughly like the expectation there, and how much it's allowed to vary overall, then this makes for a pretty good inequality. And again, if you think of c as just some constant, so for example, our original function that we looked at was actually 1 Lipschitz, right? We had some of these different coins, and changing anyone only changed it by 1. Or more generally, if they were weighted with c, then you'd have c Lipschitz. So if you think of c as some constant, this makes a lot of sense. And what's the proof of this? Well, you could just basically apply Azuma's. How do you do that? You consider the Doob martingale y0 up to yn, where you start at the expectation. So that's no information on the variable. That's the expectation, and would just be everything. And then we'll get down to the actual sample that we end up sampling, the x. So we'll have yn be x, and you think of yi is obtained from yi minus 1 by exposing xi. Right, so whatever sample we end up with, it has particular values for the trials. So what I could do is I could slowly expose the values of those trials, and then that would narrow the possible outcomes, and we take the expectations over those. So this is a Doob martingale, and it would form indeed a martingale. And now applying Azuma's inequality to this, since we kind of assumed Azuma's had to be with 0, but that's really just a technicality, I could shift this, so I could have you do y minus e of x, that would put it start at 0. And similarly, that would give you the upper tail. If you want to do the lower tail, you'd use the negatives, you'd use e of x minus y, would yield the desired result. Because then we have a martingale, and then we could apply Azuma's to these two martingales to bound how far the martingale strays from where it began, i.e. how far x strays from the expectation. So that gives you McDiarmid's. There's actually, again, a more general version where you're not C Lipschitz, but CI Lipschitz. So if you assume that trial xi only changes it by CI, instead of C squared, you get the sum of the CI squareds. And that's quite useful. So oftentimes, in a lot of the applications, it's actually quite useful just to use this more like McDiarmid's inequality, to use this Lipschitz for an actual function instead of a martingale. So this kind of nicely packages the martingale idea with the exposure to get you this kind of more general version of Hoeffding's, where I'm not some sum, but I just depend. And this is an incredibly useful inequality that can be used in lots of instances. So we'll be looking at in the future at some of the applications. Next time we'll be looking at Talleyrand's inequality, which generalizes this as well, and will give it a somewhat different proof of it, which will deal with this issue about, so far all of these inequalities involve the denominators kind of having an n, where n was the number of terms or the number of trials. And really in the beginning I said we wanted the expectation in there. And we got that for Chernoff bounds when somehow they were Bernoulli random variables, but we want that more general. So that will be next time. Today we covered the beginnings of concentration inequalities with Chernoff Bounds, Hoeffding's, Azuma's, and even McDiarmid's here. And again, concentration inequalities are one of the pillars of probabilistic methods, right? So our pillars were linearity of expectation and the local lemma, and now we have also concentration inequalities. So we want to use linearity of expectation. We often want to show that things are concentrated around their expectation to invoke either upper bounds or the Lovász local lemma. And that's what concentration inequalities will do, and we just need to have some assumptions on that. And so here, for example, C. Lipschitz would do it for you there. So that's all for today. Until next time, see you then!